uh, really on time. Yeah. So again, once again, I remind you the uh, 3G rules that we have to abide for. And yeah, okay. So today we are starting with lyases. We have already covered the three first classes of enzymes. Today we're doing number 4, 5, 6, and 7, hopefully, if time goes according to plan. And yeah, let's start with lyases. And the main thing you have to remember for lyases is they are enzymes that form bonds or cleave bonds, but in a very, very specific way. Because in lyases, you will have the case where you will either require just one substrate, such as the case here, down in the lower example. Let me go back. There we go, better. Here in the lower example, you have a compound that generates or is cleaved to produce two products, or we have two substrates creating just one product. If you remember going back to hydrolysis or yeah, um, oxidoratases, you have the case where two substrates create two products, and this is a very very consistent difference that we see among enzymes. Lyases are characterized by that. They create a bond or they cleave a bond, but they involve a reaction of either synthesis or elimination. Synthesis reactions are where two compounds, so A and B, create a third one, C, or elimination, where A degrades or decomposes into B and C. And these are very, very important reactions because each and every one of you right now is conducting multiple lyase catalyzed reactions because in the end, these are the basis for anabolism and catabolism, the two main components in the metabolism of any living organism. So these are very important in biology, and if humans have been good at doing anything throughout history, is copying biology to make processes better and more efficient. So I will skip this for now. Once again, as a repetition, they cleave carbon 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 oxygen or carbon nitrogen. There are some others, but mainly it's those three: carbon 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 oxygen carbon hydrogen carbon nitrogen bonds. And since they cleave a single bond, let's remember that carbon likes to form four bonds. Once you remove one, a corresponding proton will also be detached often, leaving the cleaved molecule with a double bond. This means that it will be unsaturated. Uh, Once again, the reverse reaction is also possible. We can start with an unsaturated substrate that will create two saturated products. And this is very, very important because an unsaturated bond or a double bond in particular is a very, very good place for further reacting because we have that pi orbital that allows us to add some other functional groups, um, yeah, making a whole new host of different products. So I want to start with an example, and this example is really remarkable. It is fairly um, special kind of lyase because if you notice, it is not a 2-to-1 reaction, but rather a 3-to-2 reaction. And in this case, we have fairly simple molecules. We have here catechol, pyruvic acid, and ammonia, that all three together combine to form this rather complicated looking molecule, which is called L-DOPA, and a residue of water. This is an actual process done by Angibottle, the Japanese company. And why, you might ask, why is this important? Why do we produce this compound? Well, has any one of you ever heard of, okay, so I'll do a quick tangent. I promise I'll try to be short and to the point. But I find this extremely fascinating, and the case of L-DOPA is truly remarkable. Has any one of you ever heard of encephalitis lethargica? Encephalitis lethargica is a disease which the first cases were studied, or actually studied, in about 100 years ago. It was just over 100 years ago. It was the start of the 19th century, sorry, 20th century. It was 1917. First World War had just happened. People were, yeah, very discouraged about life in general. And some cases, this was also the period after the 1917 pandemic, influenza pandemic. And doctors started seeing some cases of this disease where people would start being, I think, very hyperactive for a while, and then all of a sudden they would go dormant. It would be like they would fall into sleep, but they were not sleeping. They were conscious. They were aware of their surroundings, and they were kind of like prisoners of their own bodies. They could not move. They could not speak. They could not interact, but they were there, and it was possible to see their pain, their discomfort. This was studied by a guy called Constantin von Economo. I think he was British, and he described this disease, and it was an epidemic that cost the life of countless around the world. And to this day, we do not know what caused the disease. It is one of the. It has been described as one of the biggest mysteries of the 20th century in terms of medicine. And it's even more curious because it was found that the symptoms and the way it manifested, for some people, it was very reminiscent of Parkinson's. So people decided to treat the disease with a common Parkinson's treatment, which is precisely L-DOPA. And the improvement for the patients was immediate. It was overnight. Patients that were originally motionless and bedridden, they would have overnight improvement to the point where they could walk and they could talk and they could act normally after receiving the drug. It was as if the doctors had made a miracle. However, this is sadly, this is real life. This is and if things go better than expected, there's some catch there. And the catch precisely is that while L-DOPA was very effective at treating the disease, the body quickly develops resistance or tolerance to the drug, and you have to gradually increase the dose for it to have the same effect. So all of the patients who were treated with L-DOPA eventually grew resistant to the drug, and they could no longer receive the benefits of it. Unlike patients who suffer Parkinson's, who can actually take the drug and overcome the symptoms, this was not the case for encephalitis lethargica. And yeah, they all reverted to their previous state, and there was no other treatment that could help these patients. And yeah, that is basically the history of a quick overview of encephalitis lethargica and how L-DOPA was a miracle drug until it was no longer. If you want to learn more about this, I highly recommend reading about encephalitis lethargica. It is truly a fascinating history, and it's still a mystery to this day. So yeah, okay, back to our class. Another very critical thing about this enzyme that we have in the presentation right now is that it creates from three compounds which are not chiral per se. They create an enantiopure compound. So all of the product is it is only this chiral molecule. So it is really effective. You can see that the capacity of this process is 250 tons per year, which is rather large in terms of production. Right. So another example we have here is the production of a compound called neurominic acid. Neurominic acid is it's a glycoside derived from another sugar molecule that we call I forgot the name. N-acetyl-mannose. When it's combined with pyruvate, it produces neurominic acid. Now, this is a very particular glycoside because it is found at the very end of multiple structural and structural components in cell membranes, and it acts as along with other sugar residues, it acts as a receptor in many cases, and it allows that communication between cells, between the immune system, and it allows also the identification of bacteria that can be pathogenic, so that the body can attack them, or it can identify good bacteria and it can allow them to remain there. It doesn't react against them. Is a personally relevant reaction because I personally am working, I'm doing my PhD on this reaction specifically. And yeah, it is a really interesting reaction, the way it can incorporate the pyruvate molecule into a single product without the need for cofactors or any other side any other molecules that would generate side products. That is one of the reasons why lyases are often an attractive choice, because when you combine two molecules to produce your single product, you don't have to deal with any byproducts or side products that could be difficult to handle during the stages of downstream processing. So that is why they are usually very attractive in industry. This is a reminder for you. When we have a double bond, it is often the case that we have to assign the nomenclature the um, of the prochiral molecule using the Re and C phases, depending on the Can-Ingo Prelog nomenclature and order of the substituents. And this will allow us to identify, yeah, in which side of the molecule the attack happens, to create the chiral molecule. As a reminder, as I said, the Re phase and C phase are related to the planar order or planar structure of the molecule. And it is exactly the same rules that we follow for naming chiral molecules in 3D space. The only difference is that here we're looking at flat molecules. And when we're looking at flat molecules, we have only two sides. And the C phase is the one we are looking at if the order goes counterclockwise. And the Re phase is if the substituents have an order of being clockwise. So choosing this left side example, we can see that the priority would be oxygen 1, then the methyl 2, and then hydrogen 3. The order is, if we're looking at it from the top, the order would be counterclockwise. So this is the C phase, and the reverse. If we flip the molecule, then we have the Re phase. Same applies for any other compound and double bond. And once we add the molecule, we no longer have a double bond. We will eventually produce, or often with the examples in this presentation, you will produce as a chiral molecule. And yeah, when you have a chiral molecule, then you no longer have Re and C phase because you have now a tetrahedral configuration, and then we need to assign R and S nomenclature, following all the rules that you already should know. Yeah, I suggest you if you don't, then give it a look and yeah, prepare for your exam. Good. Same rules that we have already covered. You can look at them slowly and peacefully when you have more time later. Okay, so we also, this is another example that we have. It's called a fumarase. And it is, yeah, it is in this case, we have in this case, we have an enzyme where we are producing a single product using two substrates. And in this case, the substrate has the double bond. We are adding water to create a malic acid. This is a case where we use water as a nucleophile, attacking the double bond to create an alcohol residue. And you might ask, well, yes, we use the oxygen and the hydrogen from the water, but where does the other proton go? That is the one that completes the remaining bond in the in the other carbon from the double bond. This is the exact mechanism. You don't need to learn this for the exam. It is just the order in which the electrons are shifted from the enzyme to the double bond, and then from the double bond to the oxygen to the hydroxyl residue. In the reverse reaction, as you can see, this is a reminder that enzymes can catalyze both sides or both ways of the reaction. We then have another enzyme that is quite similar because it uses the same substrate, but this time, instead of adding water as the nucleophile, we are adding ammonia to end up with a secondary amine here. And this product, we call it aspartic acid, is a amino acid, very used in industry, and of course it is. It would be ideal to have 100% yield, and that is what this process allows us to have. It is. Please be careful when you study these two, because while the two of them, both fumarate and aspartase, use fumaric acid as the substrate, only fumarase, fumarase produce, fumarase, it's sometimes the enzymes are named for the substrate, sometimes they are named for the products. You need to pay attention and be careful where, why they receive those names. But in this case, we name it after the product. It is a good rule of thumb is which one is the most expensive or the most industrially attractive compound in the reaction, and that way you can tell fairly often what is the name of the enzyme. In this case, aspartase is more attractive industrially speaking, so we call the enzyme aspartase. I will skip that. We don't have that much time. I want to cover as much as possible. Okay. So now we get to a very interesting point of lyases, because we talk about decarboxylases. The one you have in the presentation here is specifically aspartate decarboxylase. This is pretty much the same product that we had in the previous reaction. As you can see, it is a compound that has 4 carbons, 2 carboxylic acid residues, and a secondary amine. And it produces, it reacts just by itself, by being in contact with the enzyme, and the enzyme cleaves it so that it releases carbon dioxide. This is a very good example of a reaction where you have to test not only your chemical abilities, but also your process knowledge and your practical abilities, because as you can see in this reaction, and in general for lyases, it is often the case that we have 1 mole producing 2 moles. That is the definition of a lyase. And when the 2 moles produced are soluble or dissolved in a liquid medium, that's not a very big problem. However, when you have a reaction where one of the components is gaseous, then you have some issues with the operation of the process, because if we now go to Give me just a second. Okay, I will switch to the whiteboard now. You should see the whiteboard. So, what's let me do the reaction right here. You have aspartic acid being produced. Which one is it? Is this?
I can see.
You cannot see. Okay. Now can you?
Yeah.
Okay. Perfect. Thank you. If you can comment in the chat, or if anyone wants to say it out loud, which stereoisomer is this one?
Aspartic acid.
But is it R or S?
It's S.
It is S, correct. We have 1, 2, 3. S. Okay, so we have EC4 lyase, specifically decarboxylase, and we produce this compound right here, NH2 with a HOO8, see here, plus carbon dioxide. Now, what we have in this process is often we will have a plug flow reactor like this, which we feed from the bottom using a pump, and we extract the product from the top. Now, the reaction happens in a liquid environment, and it goes through the packing of the plug flow reactor. The issue that you might have here is that when the reaction is going, you will observe, you will notice that at the very top, since you have the formation of a gas in the reaction, what you will have at top is that instead of having a full volume of liquid, you will produce instead of having a liquid volume, a complete liquid volume inside of your reactor, you will create bubbles of carbon dioxide. Why would this be problematic? Any idea? Any suggestions of why this would not be ideal?
It'll reduce the effective reaction area.
Reaction area. Yes, partly, exactly, because some of these volume is also occupied by, of course, the packing or the enzymes that are in the solution. But even before that has an effect, because if you remember, for the reaction to occur, the substrate has to absorb into the particle, into the enzyme, and suffer the transformation. Before even that happens, we have a reduction in the effective volume of our reactor. So if you remember the definition of retention time, residence time, sorry, it is the volume of the reactor, the effective volume of the reactor, divided by the flow. If we maintain the flow of at the same rate, then a reduction in the flow will mean a reduction in the residence time of the reactor, And this will be translated into, if we plotted, oh, that reaction volume, exactly. Really good comment there in the chat. So this would translate into, instead of seeing a consistent, let me label my axis, always label your axis. Instead of seeing a consistent conversion throughout the volume, the operation of the plug flow reactor, what we would see is a fluctuation that would dip and would return to the standard, to the baseline. And this is due to this formation of bubbles at the top of the reactor. As more bubbles are created, we have less volume on the reactor for the reaction to happen. And what you said is precisely right. Since that volume is no longer occupied by liquid, the substrate cannot no longer reach the enzyme, and therefore the conversion of the substrate is reduced, significantly reduced. And as the volume, the bubbles pass through the pass out from the PFR, then the conversion would rise again, back up. So this is a very, very big problem. And this is putting numbers into this problem. And it's not, yeah, you're engineers, you like to actually work with quantities. Working with a reaction where a gas is produced means that in the particular case of this reaction, you produce about 50 liters of CO2 per every liter of liquid reaction mixture. So you can imagine that if we take this to an industrial scale, you have quite a bit of CO2 being produced by the reactor. So, okay. So, let me go back to the presentation. Correct. So, this is something that you will probably cover in the in tomorrow's class, or if not next week, back with Professor Lisa. But yeah, this would be how the reaction looks, and as you can see here, how do you solve? What is the solution? How do you solve this the formation of these bubbles? Usually, what you do is you add an overpressure to the plug flow reactor. What this causes is that you prevent the gas from being easily created, from easily forming in the liquid. When you have an overpressure, it is harder for the gas to pass into the gaseous phase. It remains dissolved. And there's a question in the chat. Can't we increase the pressure to dissolve it? Wow. Okay, perfect. Great. Very, very good catch. Exactly. What we do is precisely that. We increase the pressure in the plug flow reactor so that the gas cannot pass into the gaseous phase. All the reactor volume remains as a liquid. You can think of it as a bottle of soda. When it is tightly sealed, the gas is all dissolved into the liquid, and it is only after you release the pressure, it would happen here at the exit of the reactor, that the bubbles can form. But that is no longer a problem because you're no longer losing any volume in the reactor, in the reaction. Yeah. section of the process. So yeah, very good. That is exactly what we do in process-wise to prevent that from happening. Great. Okay, so another interesting example is talking about nitriles. This we covered with hydrolases before the break. Yeah, last time I was also with you. And can I? Wait. Ooh, nice. I didn't know that was even possible. That's great. Okay, so as a reminder, nitrogenases are what we call this specific kind of compound. It is yeah, any molecule that has a carbon triple bonded to nitrogen, and nitrogen, of course, has two lone pair of electrons there as well. Now, what happens with nitriles is that they are they're quite reactive because there is an imbalance of charges between the nitrogen and the carbon, and also they have these extra bonds that can be the place where more where chemical attacks can happen. Now, if you remember last class we had together, one of the examples for hydrolases was the reaction where we have a nitrile group where we add two molecules of water, and if you remember, the reaction would go something like this. You have an R, and then you add one of the molecules of water to create an amide, which would look something like this in H2, double bond here. And then you add a further water molecule, and it oxidizes all the way into an acid, carboxylic acid residue. And these all, we put it into two different reactions, but this is all catalyzed by the same enzyme. So it is an AEC3, EC3. It is a hydrolase. And this all happens fairly immediately, yeah, in a single process. It can be identified if you do a careful analysis of the intermediate formation, but in the end, thermodynamics dictates that all of the initial, or most of the initial substrate will be converted into the product, which is fully oxidized. We have a question in the chat. Christoph Volta asks, it should not. Someone was asking, will it affect the equilibrium of? Oh, okay, of the if we have an overpressure of the system. No, not necessarily, because if we were operating in a batch system, it would eventually cause the accumulation of CO2 in the liquid, and that would have a detrimental effect in the production of the two products in this case. But since we are operating in a continuous phase, or in a continuous process, then all the carbon dioxide that is produced, it is quickly removed from the system, and it basically operates in the same way where like the examples for oxido reductases, where you use what's it, acetone, where you strip the yeah, you have a propanol, you oxidize propanol to create I forgot, I'm pretty sure it's acetone. And that when you strip acetone from the system, then you're no longer limited by the thermodynamic limitation of the system. Although the person might affect the equilibrium of the reaction, one of the PFD is. Oh, okay. Yeah, excellent. All right. So great. Thank you for that. Thank you for the question. Thank you for the answer. Those are always welcome. Going back to nitrile is a difficult word. Nitrile. I have an issue with English because they change the pronunciation for pronunciation changes from the enzyme to the compound. It is kind of annoying. But anyway, nitriles and nitrilases. Here is what you have for the case where you have hydrolysis. And yeah, of course, here in this reaction, I am missing the ammonia that it is released. As you can see, we know that this is hydrolase because we have two substrates, 1, 2, and two products, 1. I can count 1, 2. So there we go. There we have a 2 to 2 reaction if we ignore this intermediate step. We can erase this, and now we have the case where now we have another, which is called a nitrile hydratase. Now, nitrile hydratase, it also acts on nitriles, but in this case, instead of going all the way to the oxidized carboxylic acid as a result, it can catalyze that intermediate step by only adding water to the substrate, and this creates, you have again 1, 2 substrates producing a single molecule, and you again create a double bond in the process, and then you would go from nitrile to an amide, and then if you wanted, if that was your objective, you can then add another EC3, another hydrolase, and combining your product, your amide, with water to produce that same carboxylic acid. Yeah, and you would in the end have the same process. Now the second one would require two enzymes, and one lyase and one hydrolase, and instead of doing it in just one fell swoop. The reason why we would like to have two enzymes instead of one is that, well, you can argue that maybe you want that intermediate product is what you want, so you would only work with the nitrile hydratase, or you want to have a more careful control of each of the processes. If your enzymes if you cannot do enzyme engineering, what you can do is process engineering to compensate for the unbalance that you might have between the enzymes. So if one of your enzymes is more active than the other one, you can make it so that the process have a better match, and they are more uh, streamlined. And that level of control is something that you cannot have doing process engineering in the first case. In the first case, you could only get that level of control by doing engineering, which, as you know, it is not that not that simple. More about nitro hydratases. Here we have it, where we are working on 3-cyanopyridine for the production of vitamin B3. This is done by the company Lonza in Switzerland, and it is a very simple but very effective way of reaching this product, this high value product. Once again, you have two substrates. You add water to this compound, and you produce a single component. No need for heavy metals, no need for cofactors, no need for any other components that might make the purification step harder, especially when we're talking about something that you are going to offer for human consumption. This is why it is fairly attractive. Another example using also nitro hydratases is precisely starting from acrylonitrile, again adding water to the molecule, and the enzyme produces acrylamide. Anyone familiar with acrylamide? Anyone can tell me what we use acrylamide for? Aha, it is in burnt food. Yes, yes, indeed. It is often a side product of partial or total charring when you leave food exposed to high heat. Some of the proteins of the amino acids will react, and they will produce acrylamide. Yes, that is correct. But aside from that, yes, it is there, and this is one of the reasons why you should not be eating completely burnt food. It is toxic for humans in large quantities, so yeah, don't do that. But otherwise, it is also found in it is a plastic. It is used for very sturdy plastics, especially like window, yeah, replacements for glass when you need something like that is transparent and is very strong, but you don't want to use glass. And the way you do it is you don't use acrylamide, but you polymerize acrylamide to create this kind of polymer. Another place where it is often used is also for analysis. If you're familiar with SDS page, a technique for analyzing proteins, it is also there. It is right there in the name. The name is SDS, sodium dodecyl sulfate. Page stands for polyacrylamide gel electrophoresis. So there you go. You polymerize this molecule to create chains of these repeating units, and you can do that because there is a double bond very conveniently there, so that can lend electrons to continue the formation of that chain. Great. Okay. Now we have another decarboxylase. As we mentioned with aspartate beta decarboxylate, this is a slightly different because in the previous one we have an enzyme that cleaves the molecule to produce CO2. In this case, we're talking about a slightly different process. So why decarboxylase? I will switch to the whiteboard here. Space. There we go. So why decarboxylate? So we have as a substrate this compound. Anyone familiar with this compound? I guess that's a no. But no worries. This is what we call pyruvate. It is a very common intermediary and very common metabolite. And when we use, in this case, pyruvate decarboxylase, which is again an EC4, what we produce is it is also cleaving the molecule. And how does it cleave the molecule? Well, you have no, I mean, sorry, let's focus on these. We're saying it's a decarboxylase. So D means it removes something from the molecule, and carboxylase it means it's referring to CO2. So where can you find CO2 in this molecule? If you notice here, well, CO2 is a molecule that looks something like this when we use the proper bond notation. And if you notice, this molecule is almost, we're one skip and a jump away from doing that same molecule here. Carboxylic acids are the only thing that is one level above in an oxidation state from CO2. CO2 is the most oxidized state that you can get with carbon. Carboxylic acids are not quite there, but they are almost there. So if we remove this carbon dioxide from the molecule, what we're left with is this part, which would be this. And where does this H go? It is right here. It detaches when the carbon dioxide is removed from the molecule, and it reattaches to the missing bond right there. So there we go. And here, yeah, this is what we would create. And this molecule is called acetaldehyde. And we create also carbon dioxide, which no. All right. So going back to the presentation. Yeah. Correct. So we use pyruvate decarboxylase in the following manner. We start with molasses, which is a combination of saccharides, it is sugars, and we allow yeast to break down those sugars. The breakdown of those sugars yields precisely, I just said it, acetaldehyde. And if we combine this acetaldehyde with benzaldehyde, it is also, if you notice, it is the same structure, just bonded to an aromatic ring. When we combine these two aldehydes, the enzyme pyruvate decarboxylase can do the synthesis of an enantiopure component that we call phenylacetylcarbinol, or PAC. The R, if we select the right enzyme, we produce the R enantiomer of that. And once again, you will say, Fernando, why is that important? Why do I care about that? Well, that is the precursor, that is the starting point for the formation of a very, very used drug called ephedrine. Ephedrine is a pharmaceutical component, pharmaceutical product, very high value, and you can understand why if you notice that it has two different chiral centers, and this means that we can start with a extremely cheap source of material, raw material, which is molasses, and you can produce a very, very high value component from it. And it is all using three steps in the process. So you can see it is very, very attractive. You do not create, you are creating only the enantiopure, or the component that you want in this case, without having to deal with the separation of a racemic mixture, or having to do kinetic resolution, for example, which would imply a lower yield. And you can do it at fairly high capacity. This is using whole cells, and it is done by Krebs Biochemicals. Right. Full disclosure here, when we say, or in this previous reaction, you would need this cofactor that we see here in your screen. This is a cofactor called thiamine diphosphate, and some of the lyses in the used in industry consume this cofactor. It is necessary for the enzyme to be on its active conformation, but we do not count it, or it is not as relevant as the cofactors that were used in oxidoribophases, because this one is, for one, it is not as expensive, and often since it is not as expensive, it can just be added to the process, and then once it's done, it is no longer, it is separated, and it's no longer important. It doesn't require that recirculation, or that renewal, for it to be an economically feasible procedure. Yeah, okay, so here you see another case of a decarboxylase in action. Here you have a component where the carbon dioxide is removed, that last carbon is stripped from the chain, creating benzaldehyde, and then the benzaldehyde is combined. It is a previous reaction that we had. It is combined with acetaldehyde to create, the precursor for multiple drugs. The reality is that we have, thank you, Zainab. The reality is that we do not start with this compound in your left, because that is also a very expensive compound to create in the lab. We start with this intermediate, with benzaldehyde, which is simpler and easier to produce. We combine it with acetaldehyde in the previous way, where we start with molasses, very cheap, very easy, very convenient, to create that precursor. That is the way this process is often done. How are we doing in time? Time-wise, okay. I will speed forward. I will skip this following section. This is just analytically how we can determine different ways of how to add substituents to an aromatic ring. Still talking about carboxylation. Of course, decarbonylation is one part of one way of viewing the reaction, but also we could have the reverse process, where we can have the addition of carbon dioxide to a molecule to expand or increase the length of that carbon organic compound. And this can be done in multiple ways. You can start with carbon dioxide to produce alcohols, to produce, you can combine them with ammonia to produce urea in this case, a very attractive process. You can combine them with cyclical oxygen rings to create this compound here. It is often called a platform chemical, very useful for multiple other industrial processes. Or, as we discussed already, you can combine it with phenyl to have aromatic compounds with different substituents. These processes are very attractive. So much so that we do it. We do them industrially and at large scales, even though they require high energy inputs in terms of high pressure and high temperature for them to be effective, to actually happen. We have to overcome that limitation where we are going from an extremely oxidized component, and we want to make it so that those double bonds that the carbon creates with the oxygen are broken, are free, and we can use the potential for new bond formation of carbon to bond it into different components. The appeal is not only to produce these chemicals, but also further regioisomers. However, the problem that we have chemically is that chemical transformation or chemical reactions are not stereo selective, and they have incomplete conversions. So the annoying part of this is that nature does this same process without requiring high pressures and high temperatures. If you go back to plants, for example, plants take up oxygen, carbon dioxide from the atmosphere, and they can produce alcohols, or they can produce urea themselves. and it is frustrating because they do it at ambient pressures and ambient temperatures. So what we want is to have that same power to be able to create reactions where that is possible at milder conditions. But so far we have been unsuccessful in doing that. And if anyone could create these processes at more um, yeah milder conditions, it would definitely completely revolutionize the industry and industrial production in a large scale. Um, there's a lot of studies and research destined into the production of these kind of reactions. Some are more successful than others, uh, but of course, none have been as successful as we would like. Otherwise, we would live in a very different future. Um, one of the examples of this is um, the carboxylation of this component right here. Um, what we have is we can. Um, this was done by a colleague of Professor Lisa. And what we do in here is, yes, we start with the molecule which we want to add that extra carbon, and you can have multiple ways of catalyzing and allowing the reaction to happen. You can start with, of course, you have an aqueous solution, an aqueous media, and you can. One idea could be bubbling CO2, or let's start simple. You just have carbon dioxide and carbon dioxide at an overpressure in the gas phase above the liquid. If you do that, you would find that at a pressure of 50 bars, which is half of what we had in already installed processes, half of the lower limit of that 100 bars. So if you do it at 50 bars, you have a maximum conversion of 5%, which is, of course, industrially garbage. It doesn't work. And even if you go closer to that lower limit, to 80 bars, you have a maximum conversion of 7%, which is a non-starter. You cannot do anything productive with that. Another idea you could pitch could be, well, maybe the interfacial area is not enough. Maybe having that extra carbon dioxide on top of the liquid does little to nothing for all the enzyme that is in the bulk of the liquid. So how about we put it into more contact, into closer contact? And of course, one idea could be bubbling the gas through the liquid. And what you get if you bubble that CO2 through the liquid is even lower conversion. This could be due because the enzyme can only operate when it is liquid, and having gas going through the column causes some of the enzyme to be exposed to gas instead of liquid, making them inactive. So of course, that would result with lower production, lower conversion. Another idea could be, well, maybe we can have an overpressure and add carbonic acid to the liquid. But that would only reach again the same 5% conversion. So okay, the best we could do, the best this research team could do, was with an overpressure of 80 bar and dissolving bicarbonate, so not handling carbon dioxide as a gas, but rather the bicarbonate ion, which is what happens when you dissolve carbon dioxide into a liquid. You add water in. Let me do the reaction here. So if you have CO2, you dissolve CO2, so it is in the liquid. You produce, and this will be governed by equilibrium. You produce HCO3, which is the bicarbonate ion that you have right here, and this is soluble. You can dissolve this ion into a liquid, and I want to do emphasis in this reaction because it is what happens in your blood. This is how your tissue gets rid of CO2 from the cells in your body to the environment. It uses bicarbonate to flow to dissolve it into your blood, and then from the blood it passes into carbon dioxide once it reaches the lungs, and that's how you exhale it. So in this case, when you have bicarbonate in the liquid, you can have a maximum conversion of 25%, but of course, compared to the industrial processes, it's nowhere near what you would need for it to be economically attractive or feasible even. So yeah, we have a lot of way to go. There is a lot of improvements that can be done for this process to be achieved. And we're still learning and still developing a lot in these terms. Another appealing part of this process is, of course, if you can capture CO2 from the atmosphere, which is part of the reason why we have climate change in the first place. If you could use that excess carbon dioxide and put it back into compounds, useful compounds in the industry, you could harness that. Have a process that could be that could have a negative carbon footprint, for example. So there is also an incentive in that regard. Even despite all these incentives, we have not been able to come up with a process yet. We'll see what the future has has in store for us. Part of the reason why it is very difficult for carboxylation reactions to happen is that we're going against the thermodynamic equilibrium. Carbon dioxide is extremely stable, and its Gibbs free energy is really low compared to any other component that you can have. Because it is the most oxidized, especially in an oxygen-rich atmosphere. It is the most oxidized that carbon can be. It is very stable. It has two symmetric double bonds on each of the sides, so it is basically it is often called inert for that reason. If you wanted to overcome that barrier, you would reach a state where you will have compounds that have an energy level that is often over that of carbon dioxide, meaning that thermodynamics will always push those compounds that you produce back to producing CO2. And again, once you create CO2, it doesn't stay much in a liquid, so it will degas, it will go back into the atmosphere, and you have once again the same problem that we have discussed previously. So yeah, this is a schematic of the reaction when you go with thermodynamics. So if you release CO2, the reaction is very easy to complete. However, if you run the reverse process, you will often hit a wall, and that wall is the limitations established by thermodynamics. Okay, let's go quickly. This class ends at 2:45, right? All right, so we have 15 minutes for 3 enzyme classes. Can we do this? Let's find out. One last example that I wanted to quickly add to that in the growing list of liases is what plants use as defense. It is also dealing with nitrile, but in this case, it is a specific configuration where you have a nitrile group close to an ether bond, and which has a sugar in there. Plants cannot move, so they have to rely on chemistry to defend themselves. Often this is done by creating, not letting sugar stand by itself, but rather attaching it to security devices. It is as if it acted as a lock to your bicycle when you leave it in the street. Why is this all? Well, if you can successfully obtain or extract the sugar from this molecule, then you will have a compound that is often degraded. It is fairly easy to degrade using common enzymes in the body, and this releases hydrogen cyanide. Hydrogen cyanide is extremely potent toxin. It causes, it jams the cellular respiration, and it at fairly small doses, it can cause death. So it is a way where it is a way for plants to avoid being eaten by other organisms, something including us. This is also a reaction worth stopping because it is the first case of asymmetric biocatalytic reactions done in a chemical lab. What was done is this compound right here, benzaldehyde, was left in the presence of emulsin, so crushed bitter almonds, and it was exposed to hydrogen cyanide. And the person who was doing this, Rosenthaler, found out that if left there at room temperature, the resulting mush had a high concentration of this specific enantiomer, but not the other one. And it was later found out that this is due to the action of hydroxynitrile lyase, which is the enzyme present in bitter almonds. Different plants have different selectivities. You can have R selective or S selective, depending on the specific way where how the plant decides to store that sugar, or keep it safe from predation. This in particular, I don't know why this is. Anyway, and of course, this reaction can be harnessed in the reverse order, where instead of producing a toxic compound, we can use it as a reactant, as a substrate, to create interesting conformations, not only because they are interesting by themselves. That nitrile group it's always has the risk of being released and causing being toxic. So instead, what we do is we use it as a platform to add different other substituents. So we have here, for example, vitamin B5, where we replace that nitro group with hydrogen, and then we have, of course, a useful compound that is safe to consume for humans, and not only safe, but also necessary. Great. Insecticides are also produced in doing this. Of course, if plants can do it, we also can. And it has a very, very broad application in industry as well. All right, so let's squeeze it right at the end. Okay, so those were lyses, very, very interesting basis for metabolism. Remember, you have one single product either produced or consumed, chemical produced. Now let's go into isomerizes. Isomerizes, sadly, isomerase, and this is three last enzyme classes that we're going to cover, are not very spoken of in terms of industry, because they have not been widespread, or they have not been applied on a very, very large scale. And the problem is either that the reactions that they catalyze are difficult to apply, or they are, we don't have a very wide knowledge about them. And it is a recursive problem. Since we don't study them a lot, then we don't have enough of them for application in industrial processes. As you can see in this diagram right here, each of them have around 100 different enzymes for each of those classes. So it's not a very big number, but still it is important for us to cover them. Isomerases, they catalyze either isomerizations or racemizations of compounds. This means that they can use, this means that often the reactions that they have is one-to-one, which is also appealing. You don't have to deal with cofactors, with other chemicals. You don't have to deal with stoichiometric ratios and so on. They're very straightforward in that sense. It is also very easy for characterization, mathematical characterization, because you have the case where it is a compound A producing a compound B. So of course you wouldn't have any cases of inhibition or obstruction of the action of the enzyme. So easy to describe mathematically, but again, not very common to apply. Different isomerases and epimerases are known, around 100, as I said. Racemases are known, but not commercially available. They're hard to study, hard to extract, hard to apply. And racemases can be used in industrial biotransformations, but they are only the result of very, very specific research. One of these examples is this case. It is a racemase. What we do is that we are producing, we're doing kinetic resolution, where we start with a racemic mixture of these compounds. We hydrolyze it to produce this specific conformation. We hydrolyze it in the way where we open the chain. This is the product that we want to obtain. It is called L-lysine. It is an amino acid. It is very, very attractive for industry. And the unreacted compound here, we can racemize it using an enzyme to again doing returning it into conformation that can actually react to form that lysine product. So that is a way of how we can take advantage of racenases into combining them with kinetic resolution into what we call a dynamic resolution. And this process, I think we have already covered before, but this allows us to go from what the standard theoretical maximum, that is in kinetic resolutions 50%, all the way to 100%, if theoretically at least. We will skip that. This is another close to home because I do work with this enzyme as well. It is also it is an epimerase. It changes the position of this residue of amino acetyl amino group, functional group from equatorial plane into the axial plane of the sugar ring. You don't need to learn that, but yeah, it is also a possibility in specific research. Another example is glucose isomerase. We use it for the production of high fructose corn syrup, starting from glucose. Fructose is sweeter than glucose, and it is often used as a sweetener, but also as a preserving agent for a lot of food items. And right in the nick of time, we will cover ligases. Ligases are very similar to liases, precisely. The names are a bit of a problem there because they are very similar. But ligases, the difference is that they operate under energy consumption. They require ATP for catalyzing their reaction. And that's why if you have the option of catalyzing a reaction where you create a bond either without ATP or with ATP, you will often go with the one that does not require you to use ATP for the reaction to be completed. ATP is a very expensive cofactor, so of course, if you don't need it, you will not use it. And the only, not large scale, but common or familiar example that we have right now is practically the reason why we are doing this online in the first place, and it is applied to PCR tests, because the enzyme that does the replication of that RNA strand requires ATP for matching all the base pairs in a genetic sequence, and this allows the increase or I forgot the word, the transcription reaction to take place. Allowing you to have a decent amount of the viral genetic code and make the identification easier. Where are in the reactions on slide 63 no E5 shown? Instead it shows okay, let's go back to that one. 63 you said. I do not. That's a good, very well spotted. That's a mistake. It should be E5. It's in this case E2 stands just for an identification tag. This enzyme is an E5, but here we're just naming them E1, E2, depending on what we have. actually this enzyme right here is actually not an oxidoreductase, as you can imagine. It is a hydrolase. So yeah, you add water, you produce the hydrated products. The racemization is done by enzyme 2, which is a racemase, and racemases are part of isomerases. That's why. I hope that was a clear explanation. Finally, the last before I let you go, the last type of enzyme is translocases. They are used for the transport of substances through a membrane. The reason why we don't use them is because they are embedded into a membrane, so it is very hard to produce that, not only the enzyme, but also the enzyme with the membrane, so we can handle the process. And they often also use ATP to be active. So again, like ligases, they are not ideal for large-scale processes. All right, so whew, sorry I took 3 minutes extra from what was planned. Thank you very much for being here. Thank you very much for your questions, for your attention. I hope everything made sense. If not, you can contact me. I will try to respond for my mistakes. I hope you have a wonderful day, and thank you very much. Sorry again, this has to be done online. Tomorrow, Professor Lisa will take over again, and yeah, have a wonderful day. See you next time. Yeah, good.